Today we will speak about generator and motors. The definition of electric generator is a device that produces electric current from mechanical motion. A simple generator consists of a loop forced to rotate in a fixed magnetic field. The force that causes the loop to rotate can be supplied by hot steam running over a turbine, as occurs in nuclear and coal-fired power plants. On the other hand, the loop can be made to rotate by flowing water or wind to generate electricity in a pollution-free way. There are two kinds of generators: alternating current generators, AC, and direct current generators, DC. In a direct current generator, the rotating loop is connected to an external circuit through a split commutator ring. As the loop turns, the connection is reversed twice per revolution. So, the induced potential difference always has the same sign.
An AC generator consists of field magnets, an armature, two slip rings, and two carbon brushes. The poles of field magnets are concave and cylindrical in shape, and therefore produce a radial magnetic field. Armature is a soft iron core on which a coil having a large number of turns of copper wire is wrapped. The two ends of armature are attached with two slip rings. These rings rotate with the coil. The slip rings are made of metals and are insulated from each other. Two brushes are made of carbon. One end of each brush is in contact with rotating slip rings, and other end is connected to an outer circuit. A galvanometer is connected in the outer circuit to show the deflection due to the current induced in the armature. When coil is rotated between the pole pieces, a current is induced in the coil. The induced current is shown by the deflection in the galvanometer. The two-way deflection in the galvanometer shows that the induced current is alternating. Now let's see the working of an AC generator. The armature keeps on changing its relative position with respect to the magnetic field as it rotates about an axis perpendicular to the field. Therefore, the flux linked with the coil keeps on changing with time. As a result, an EMF is induced. This in turn induces an electric current in the coil as the two ends of armature are connected to an external circuit. An electric current starts flowing through it. The current is detected by the galvanometer connected in the external circuit. Due to change in the relative position of the armature coil, the direction of the current flowing in each arm of the armature coil keeps on changing, and hence the current so obtained is alternating current. To understand the generation of alternating current more clearly, let us mark one arm of the armature as green and the other as pink. As per the Fleming's right-hand rule, the direction of current in the arm marked as green is outward, and in the arm marked pink is inward. After rotating half turn in anti-clockwise direction, the direction of current in green arm becomes inward and that in the pink arm becomes outward. Thus, after every half turn, the direction of current changes, and as a result, alternating current is generated. If we plot a graph between the induced EMF and time, we will observe that the induced EMF shows sinusoidal behavior. It can be seen from the graph that the direction of the current keeps on changing with time, which again alternating nature of induced current.
I think you know that an alternating current AC is a current that varies in time between positive and negative values, with the variation often showing a sinusoidal form. In the AC generator, each end of the loop is connected to the external circuit through its own solid slip ring. Thus, this generator produces an induced potential difference that varies from positive to negative and back. Alternator. It is a generator device that produces alternating voltages and the resulting alternating current. The device in figure could also be used as a motor by supplying a current to the loop and using the resulting motion of the coil to do work.
You can find DC motors in many portable home appliances, automobiles, and types of industrial equipment, and the operation and construction of a commercial DC motor. Let's first start with the simplest DC motor possible. It looks like this. The stator provides a constant magnetic field, and the armature, which is the rotating part, is a simple coil. The armature is connected to a DC power source through a pair of commutator rings. When the current flows through the coil, an electromagnetic force is induced on it according to the Lorentz law, so the coil will start to rotate. You will notice that as the coil rotates, the commutator rings connect with the power source of opposite polarity. As a result, on the left side of the coil, the electricity will always flow away, and on the right side, electricity will always flow towards. This ensures that the torque action is also in the same direction throughout the motion, so the coil will continue rotating. But if you observe the torque action on the coil closely, you will notice that when the coil is nearly perpendicular to the magnetic flux, the torque action nears zero. As a result, there will be irregular motion of the rotor if you run such a DC motor. Here is the trick to overcoming this problem. Add one more loop to the rotor, with a separate commutator pair for it. In this arrangement, when the first loop is in the vertical position, the second loop will be connected to the power source, so a motive force is always present in the system. Moreover, the more such loops, the smoother will be the motor rotation. In a practical motor, the armature loops are fitted inside slots of highly permeable steel layers. This will enhance magnetic flux interaction. Spring-loaded commutator brushes help to maintain contact with the power source. A permanent magnet stator pole is used only for very small DC motors. Most often, an electromagnet is used. The field coil of the electromagnet is powered from the same DC source.
Many closely spaced loops are employed to make more efficient use of the rotational motion. Multiple loops also resolve the problem that a simple one-loop motor could stop in position where current through the loop produces no torque. And now it's time to talk about regenerative braking. Hybrid cars are propelled by a combination of gasoline power and electrical power. In a hybrid car, when the brakes are used to slow or stop the car, the brakes are connected to the electric motor, which function as a generator, charging the car's battery. Thus, the kinetic energy of the car is partially recovered during braking, and this energy can later be used in order to propel the car, contributing to its efficiency and greatly increasing its gas mileage in stop-and-go driving.